Okay, good afternoon, everybody. It's my pleasure this afternoon to introduce my student Kay McMonigal. And Kay has been here at Rosenstiel School since 2015. He was an undergraduate at Northwestern University, where he got 3 majors and a minor in mathematics and earth sciences, integrated sciences, and gender studies. And other notable achievements of Kay's graduate career so far are that Kay's been on 3 cruises, including on 2 South African vessels. At least both of those cruises pretty challenging, and as it turns out, the 3rd cruise that he joined on a US vessel down to the Antarctic was also pretty challenging, on behalf of vessel pieces falling off and going wrong, and bad weather and so on. He founded a group here at the University of Miami for LGBTQ+ in STEM. It's called OSTEM at UM, and it's open to everybody, students, staff, and faculty across the university. Kay taught a honors course in dynamical oceanography, basic steady-state ocean dynamics at the University of Cape Town for their undergraduate honors program, on his own, staying in Cape Town, and that was an enormous achievement too. What else has Kay achieved? He's weathered 2 major hurricane threats to Miami. One of which, I think the first one you stayed here for, and I evacuated, and the second one, Kay evacuated, and that turned out to be not such a great plan, because some of you may know that he suffered an accident in Chicago where he evacuated to. So sometimes I guess things are going to get you. But Dorian didn't get us all, so. Yeah, I think I've probably covered everything, and so now I hand over the floor to Kay, and he's going to talk about estimating a time series of South Indian Ocean meridional heat transport.
Okay, thank you, Lisa, for introducing me. My committee members are Lisa, as well as Shen Elipo, Igor Kamenkovich, Rena Fine, and then Josh Willis at the Jet Propulsion Lab. So I'm going to start off by saying, as Lisa mentioned, it was a very eventful semester. So when Hurricane Dorian was coming to Miami, I flew up to Chicago with my partner, and we got run over by a Tesla Model X in a crosswalk. So I wanted to start off my talk by saying thank you to Shannon, who took care of me, even though she also got hit by a car, as well as thank you to Jen Stone, Sean Kennelly, and Rena Fine, because I couldn't really live at my house. I couldn't get into my office. I kind of thought about taking like a leave of absence or something, so I don't think I would be here giving this talk this semester without help from all of you. Okay, so let's start with an outline. I'm going to start with an intro of why do we care about ocean heat transport. Then I'll go into the Agulhas Current. Then we'll talk some about the full basin heat transport, and as part of that, I'm going to discuss the South Indian Ocean interior, and then go back to the full basin heat transport for future works. So the overarching idea here is ocean heat transport, and the ocean and the atmosphere both transport heat because there's an excess of heat going in to the planet at the equator and a deficit at the poles. So without this, the equator would continue heating up and the poles would continue cooling down, and we know that's not happening due to this heat transported by both the ocean and the atmosphere. And we can directly calculate ocean heat transport by taking the integral over space and over depth of the specific heat capacity of the ocean, the density, the velocity, and the temperature shown there. And we're going to take the heat capacity times density as a constant, which is what has been done previously. And when I say temperature here, I'm talking about potential temperature, so we will have removed any of the effects of pressure. Why do we care about ocean heat transport? One reason that we care is that the ocean has absorbed more than 90% of the excess heat due to global warming. So this is a figure from the IPCC report, and it shows the energy absorbed by different parts of the climate system since 1970, and you can see the vast majority has gone into the ocean, mostly in the upper ocean, but also some in the deep ocean. And if you looked at a map of this, it's also spatially non-uniform. So some areas of the ocean are warming more than others, and this might have to do with ocean heat transport and heat converging or diverging in different places. And those convergences and divergences of heat can also have local weather impacts, so things like storm tracks, for instance. It's worth noting that it's much easier to measure volume transport than heat transport. And this is because of the correlation between temperature and velocity. So if we only want to measure volume transport, we could have endpoint moorings and get an integrated volume transport between 2 points. But if we want to calculate heat transport, we could decompose our equation into a term with the spatial mean velocity and spatial mean temperature, but we're also going to have a term that's related to the correlations between temperature and velocity. So practically, this means that we need to measure both temperature and velocity at high resolution with small errors to get an accurate picture of what's happening with ocean heat transport. And ideally, we would want to determine how the heat transport varies with volume transport so that we don't have to continue measuring both temperature and velocity. And so that's kind of one of the large-scale goals of what I'm doing. We can look at a picture of the global ocean heat transport. This is from Lumpkin and Spear, 2007. And these units here are given in petawatts, which is a large amount of power. So a petawatt is 10 to the 15 watts, and that's the same as 300 times the average US power usage, or the power of 2.5 billion Tesla Model X's, or the power of 1 million nuclear reactors. And so basically the ocean is moving around an enormous amount of heat. And we can see that generally speaking, ocean heat transport tends to be poleward, although in the Atlantic it's northward everywhere. And to get that it's generally poleward, you also have to consider the Indian and the Pacific as a combined system. So the key question of my dissertation is how much does this number across the South Indian Ocean vary? We have that it's 1.55 petawatts here, but that's based on data at one point in time. So that doesn't give us a very good idea of the variability. It actually doesn't give us any idea of the variability. And to try to get an idea of what we might expect, we can look in the North Atlantic at 26.5 north, and broadly speaking, say that the heat transport there varies a lot. So if we look at the heat transport, this is from the Rapid Mocha website. It's the black time series here, and we can see this mean value of 1.24 petawatts. Was not a bad approximation of the mean for this time series, but we have a lot of variability too. So the heat transport's sometimes as low as half a petawatt and sometimes as high as 2 petawatts. And the reason I'm comparing to Rapid Mocha is it's the only observational time series of ocean heat transport, including a western boundary, in a way similar to what we're doing. So I'll compare back to Rapid at a few points throughout this talk. Okay, so looking at the South Indian Ocean, I'm going to be talking about the South Indian Ocean across here, and so I'm going to talk about the Agulhas Current, and then I'll talk about the interior of the South Indian Ocean. By that I mean everything to the east of the Agulhas Current. So we have the Agulhas Current flowing southward along the South African coastline. There's Agulhas leakage that goes into the Atlantic. We also have the Indonesian through flow bringing water from the Pacific into the Indian Ocean. So we could consider this whole thing part of the Atlantic Indo-Pacific supergyre, as it's called here, or the Southern Hemisphere supergyre. So we can think of the South Indian Ocean heat transport as the two different sections, as I already mentioned. So the first section, the western boundary, which is the Agulhas Current. And this is an area that's very narrow, it's highly variable, it's pretty shallow, it's confined close to the coast. And because of all those things, we can't resolve it using Argo floats. So what we're going to do is we're going to use moorings in the Agulhas Current. In contrast, the interior is huge. It's about 10,000 kilometers wide, so there's no way you can put moorings across the whole thing. And broadly speaking, you can resolve what's happening with Argo and satellite data. It's all deeper than 2,000 meters, and it's not quite as variable as the Agulhas Current. I will note we're not resolving the mesoscale. We're doing a quarter degree by quarter degree mapping here. So there is some assumption involved that the mesoscale is not important in the heat transport. So in the interior, we're going to use Argo and satellite sea surface height. So historically, how you would measure ocean heat transport is take a ship across an ocean basin, taking CTD stations, measure geostrophic velocity, temperature, conductivity, and other properties, and come up with the ocean heat transport at that particular point in time. And then this project, which is called the Agulhas System Climate Array, or ASCA, with a nice logo up there, and it's a collaboration between the US, South Africa, and the Dutch. And what we're going to use Argo floats across the interior, microcats and current meters on our moorings, and then CPIs, which measure acoustic travel time. And I'll talk more about those instruments later. So historically, you would do these decadal repeats of the hydrographic crossings. In the South Indian Ocean, these were done in 1987, 2002, 2009, and then there's an upcoming crossing in 2020. And you would use this to look at long-term changes. So for instance, has the circulation changed between 1987 and 2009? Here, we're looking at temperature and velocity of the Agulhas Current and then the upper 2,000 meters of the basin interior to get a 25-month time series. And we can use this to look at seasonal and other short-term changes. And this provides a context for the longer-term changes. So for instance, when we see these long-term changes, is there any aliasing of a seasonal cycle, or do we think it's something longer-term? So I would argue that these work in tandem and that you need both of them to understand the climate system. Okay, before I go into some results, I want to make one note on heat transport. Unless mass is conserved, the absolute values of heat transport are arbitrary. So what I mean by that is you can picture if we had a slab of water that's 10 meters wide and 1 meter tall, and it's moving northward at 1 meter per second, and let's say it's 0 degrees Celsius or 273 Kelvin. And if we calculate our heat transport in degrees Celsius, we're going to get 0 because we're multiplying by 0. If we calculate it in Kelvin, we get something that is very clearly not 0. So you can see that in that case, our choice for what counts as 0 in the temperature scale makes a big difference for what we get in heat transport. In contrast, if we had a 5 meter wide slab traveling northward at 0 degrees Celsius, and then a 5 meter slab traveling southward at 2 degrees Celsius, so that's 273 and 275 Kelvin. Then when we calculate heat transport, the first term here is from our northward velocities, and then we get a negative from our southward or negative velocities, and we get 2 rho Cp. And in Kelvin, we end up getting the same thing. So in other words, when mass is conserved, these values are no longer arbitrary. So I'm going to call this integral for heat transport, temperature transport, when mass is not conserved. That's what previous authors have done, and that's just to make it clear that it depends on our temperature scale that we're using. I'll talk about it relative to 0 degrees Celsius, and the variability is meaningful even though the absolute values are arbitrary. Okay, so going on to our first piece on the Agulhas Current. This is an in-prep paper on the observed modes of Agulhas Current temperature variability. And that's Cape Town there. We had a lot of collaborators based in Cape Town, and several of our cruises also left out of Cape Town. So the scientific questions for this section of the talk: how does the temperature structure of the Agulhas Current vary on seasonal and shorter timescales? How much heat does the Agulhas Current carry? What dynamic processes cause variability in the Agulhas Current temperature transport? And how well can we estimate the temperature transport of the Agulhas Current only using the volume transport? So in other words, do we really need to measure temperature, or can we just measure the volume transport? So motivation for this: the temperature of the Agulhas Current has been shown to impact local weather, including extreme events and rainfall over southern Africa in several papers. The Agulhas Current is also a warm and fast current, and so likely it dominates the basin-wide heat transport. And this is also the first time series to resolve the temperature structure of the Agulhas Current, so we should take a look at the modes of variability and see what's happening in the current. So one mode of variability we already know happens in the Agulhas Current is meandering. So typically the current is confined fairly close to the coast, but some of the time it will move much further offshore and have a path like this. In the mean, this happens 1.6 times per year. And you can see it from subsurface data, and you can also see it from surface properties. So here's an example in sea surface temperature. When there's not a current meandering, the warm temperatures that are within the current are all very close to the coast. And during a meander, those temperatures move offshore, the warm temperatures. Okay, so our methods, we had 7 tall moorings and 5 sea pies. So the tall moorings were instrumented with 56 microcats, and those are the green instruments shown here. There were also 25 current meters shown in red, 7 ADCPs at the top of each of the tall moorings, which measure the current velocity from where they're located to the surface. The 5 sea pies, which are the purple along the bottom here, and they measure acoustic travel time, which you can use to get geostrophic velocity and temperature and salinity profiles. And then the Gimpy SST product, which is a quarter degree by quarter degree gridded sea surface temperature product. And this is very similar to the instrument setup from the Agulhas Current time series, or ACT, except that ACT did not measure temperature or conductivity. So the ACT configuration was very similar, except that there were none of these microcats shown in green. So from that, the volume transport of the current could be calculated. So these are time series of the volume transport in a streamwise sense in red, and then in a boundary layer sense in gray. Okay, so what do these look like? Microcats are these smaller instruments here, which measure temperature, conductivity, and pressure. Then there's a current meter below it. ADCPs, it's that instrument that's inside of the orange float, and the float is keeping it upright. Sea pies look something like this and sit on the bottom of the ocean, and then we'll have the gridded sea surface temperature product. Okay, so unfortunately we didn't have great data return from the current meters. So here's a schematic showing in green the current meters that measured the full 25 months. In yellow, they measured about 2/3 of the time, orange is about half the time, and red is less than half. And so what we did to lengthen those records is we used linear regression with the neighboring instruments. So for instance, this instrument here, we used linear regression with the instrument at the same depth but offshore, and on the same mooring but above it, to reconstruct a full-length 25-month time series. And we can estimate how much of an error we get from this by taking the data from the ACT array and simulating as if some of the current meters did not record for the full time, as we actually saw here, and then seeing what we get in the simulation versus the full ACT array in terms of integrated transport. So that's shown on the right. So in blue is the actual ACT data with all of the current meters, and in red is the simulation where some of the current meters did not record for the full time. And what you can see is there is an overestimation of southward velocities around 1,500 meters. But the two time series, if you look at time series of the volume transports, they're highly correlated with each other. So we think that there is possibly a 5 spare trip bias in the volume transport calculated here, but we're confident that the variability is resolved well. Okay, so methods. We had to take the temperature and velocity records and map them onto a regular grid. And we did this using previously established methods. So for velocity, we did the same method that was done in ACT. For temperature, we used the temperature gradient as a function of pressure, which has been done previously in the Florida current. And then for the CPIs, we used the greatest empirical mode method, which is also called GEM, to get temperature, salinity, and velocity profiles. And some of this relied on using hydrographic data in the region. So to get the temperature gradient as a function of pressure, we used these black profiles that are within 300 kilometers of the coast. And then to do the GEM method with the CPIs, we use the black profiles as well as the gray profiles. And these come from cruises and from Argo profiles in the region. Some errors. I'm not going to go through the details of how we calculated all of this, although you're welcome to ask a question, but I'll go over some of it. So we can come up with an error in temperature by taking a hydrographic crossing of the Agulhas Current, subsampling it to where we had microcats, and then reinterpolating using the same method that we use. And this is the difference between the full hydrographic field and the subsampled and reinterpolated field. And you can see the errors are pretty big in the surface area. So above about 500 meters, there are large errors, but below that, the errors are generally speaking quite small. And that's because we didn't have very many measurements in the upper 500 meters. The mean over this whole field is 0.46 degrees Celsius. We can also come up with a current meter volume transport error of 6 spheredrops and a CPI's error of 7.1 spheredrops, following the same method as used in ACT from Beal et al. 2015. And when we combine all of these into a temperature transport error, we get errors that are 5% of the mean for the boundary layer measurement, which I'll call the box measurement, and 6% of the mean for the jet or streamwise measurement. And I'm going to define those in just a minute. Okay, a couple of definitions. So we need to define times that there were meanders. So we did this using the sea level anomaly near Mooring Sea, which was defined by Elipo and Beal 2015. And we get that there were meanders in 5 separate events here, shown in gray. And I'm going to show the meander times in gray in all of the time series I show so that you can see if the variability is related to meandering or not. We'll define the box transport as the total transport from the coast to 220 kilometers offshore, so that you could also think of this as a boundary layer definition, and the jet transport as the southwestward transport from the coast to the first maximum of the cumulative transport offshore of the jet half-width. So in other words, it's following where the current is. It's a streamwise definition. And those are also both from Beal et al. 2015. So doing all of that, we can come up with the temperature and velocity fields on 20-hour estimates. So here the colors and the thin contours are the temperature with the scale shown on the right. And then these thick contours with the numbers are the velocity. The yellow squares are where we have microcats. So areas that we have more of those, we tend to have more confidence in the temperature field. So particularly, we have less confidence what's happening up here above 500 meters. We don't have quite as many instruments. And you can see that generally the current is pretty close confined to the coast. It has peak speeds of between 1.5 and 2 meters per second. The isotherms generally slope upwards towards the coast as well, which is reflecting that southward flow geostrophically. And there's going to be a meander coming up where you'll see the core of the current propagate westward. Okay, so there was one. The core of the current came all the way out to here, and now it's moving back. And so we can use this to come up with a mean case during meandering times and during non-meandering times. So in the non-meandering case, as I already mentioned, the current is very close to the coast, and we have the isotherms slipping upwards. In the meandering case, the core of the current's much further offshore. It's about 150 kilometers offshore. The peak speeds are a little bit lower, and we can also see changes in the isotherms. So for instance, the isotherms slope upwards further offshore, and then some of them are slipping downwards back towards the coast. And that reflects that there's a weak northward flow inshore of the southward current. And the meanders occurred 9% of the time in 5 separate events, which is more than average since there's typically 1.6 meanders per year, so we could say it was a rather active time for meandering. So next we're going to look at EOFs of the temperature field, and generally speaking, EOFs, or empirical orthogonal functions, decompose a signal into orthogonal basis functions. So generally, if we just had a scatter plot of data like this and we took an EOF, it would pick out the direction of the maximum variance, or in other words, this arrow here that shows the direction that the points tend to be varying on. And so we can use the EOF analysis to see what causes variance in the temperature structure of the current. And EOFs do not inherently have to represent a physical process. This is just a statistical tool, but oftentimes they do represent physical processes. So for instance, if you take the sea surface temperature data in the Pacific and you deseason it and take an EOF, the first thing that comes out is this pattern here, which is clearly related to El Nino. So what we get when we do that is the first EOF, which describes 40% of the variance, and it has a pattern that looks like this. And so in its positive phase, we see a warming of the current, kind of where the core of the current is typically, and then a surface intensified cooling offshore of that. It's highly correlated with the meander time series. So in black here is the principal component time series, and in red is the meander time series. And you can see we have strong net values of this PC time series during meanders. And so during a meander, we get the reverse of this pattern. So in other words, we get a cooling near the core of the current and then a surface intensified warming offshore. And that's what we would probably expect from a meander because the warm current is moving offshore. So where the current was before it moved will now be colder, and then where the current now is will become warmer. The second EOF describes 25% of the variance, and it looks like a cooling kind of where the core of the current is again, and then a warming offshore, but that extends deep. And I'm going to come back to EOF2 later because it'll tie into some things I talk about in a minute. The third EOF explains 15% of the variance, and it's very surface intensified, although it does reach deeper within the core of the current, and it also reverses a little bit offshore. And if we look at the principal component time series here in black, we can see some high frequency variability, but we can also fit a seasonal curve to it and see that we generally get what we would expect in the southern hemisphere subtropics. So the temperatures tend to be warmest in about March and coldest in September, October. And this pattern is highly dependent on the sea surface temperature product. So for instance, if I don't use the sea surface temperature product, we get a pattern that looks very different. There do seem to be some anomalies that are occurring below where we do have microcat data. So potentially this deeper extension in the core of the current and the reversal at depth might actually be coming from our microcats and not just from the seasonal cycle of sea surface temperature. So next we want to understand the system as a whole, so we calculate the integrated volume and temperature transport. So the volume transport, we're going to take the integral of velocity over space and depth. The temperature transport will be that same integral from earlier for heat transport, except that we're not conserving mass. And then we can also talk about the transport weighted temperature, which to a constant is the same as the temperature transport divided by the volume transport. So this is a mean temperature of the current. So first, plotting the volume transport on top and the temperature transport below it. Here I have our box or boundary layer measurement in black, and then the jet or streamwise measurement in red. And I think the most obvious thing that you see first is that the volume transport and the temperature transport are highly correlated with each other. These time series look very similar. You can also see that generally speaking, the box and the jet measurements agree, except for sometimes during meanders, there can be large differences between the two. And we see that there's large variability in both the volume and the temperature transport. So both go almost to 0 at some points in time, and then get as large as 180 spheredrups, or almost 7 petawatts. And then we can plot the transport weighted temperature, and we see something that's also highly variable. It goes between 9 degrees Celsius and 20 degrees Celsius. It looks like it has variance on lots of different time scales. It doesn't seem to be principally varying with the meanders. So we can look at a table of the statistics from this. Here I'm just showing the statistics from the jet measurement, although you can do similar for the box measurement. So in the mean, we get a transport of 76 spheredrups southward, which is not statistically different than that 84 spheredrups found previously from ACT, from Beal et al. 2015, especially considering that some of our current meters did not record for the full time. The mean temperature transport is 3.65 petawatts southward, and that's a huge amount of heat. So by comparison, the Indonesian through flow transports a little bit over 1 petawatt, and the Florida current at 26.5 north is about 2.5 petawatts. So this is larger than either, and in particular, since it's much larger than the Indonesian through flow, this does confirm that the Agulhas Current plays a large role in the basin-wide heat transport. The volume, temperature transport, and the transport weighted temperature are all highly variable. If we look at the mean transport weighted temperature, it's 12.37 degrees Celsius, and this is a little bit lower than what had been previously reported, although this previous study was at 32 degrees south and we're at 34 degrees south, so it makes sense that we get something colder since we are farther south. And then we can also look at the means between meander times and non-meander times and see that the temperature of the current is a little bit colder during meanders than during non-meanders. Okay, so let's go back to our second EOF, which described 25% of the variance. And if we look at the principal component time series in black, we can see that it's highly correlated with the temperature transport of the current, here shown in red. So the R-squared value between these two is 0.53. And so when this pattern is positive, there's a stronger southward temperature transport. So in other words, when we have negative temperature anomalies in the core of the current and positive temperature anomalies on the offshore flank of the current, we get more southward temperature transport. So to try to figure out why that is, we can look at composites of the 10% strongest and weakest temperature transport times. So the strongest is shown here on the left, and then the weakest is on the right next to it. And we can see some differences clearly between the isotherms, but it's a little hard just staring at those two. So we can plot up the difference. And what we see is there's a very strong warming on the offshore flank of the current and a little bit of a cooling on the inshore edge of the current. And there's also positive southward velocity anomalies. Sorry, there are negative anomalies here, but there are southward velocity anomalies throughout the entire field, shown here. And so what's happening here is that we have a shoaling of isotherms inshore and a deepening offshore, and that's working to steepen the gradient in the isotherms and likely the isopycnals as well, which geostrophically would create a stronger southward flow. So we can look at the pressure of the 10-degree isotherm at 220 kilometers offshore, so that's on the offshore flank of the current, and we're using that as a proxy for the thermocline depth. And when we plot that, shown in red here against the temperature transport in black, we can see that they're highly correlated with an R-squared of 0.58. So a lot of the variability in the temperature transport can be described just by movement of the thermocline on the offshore edge of the current. And this looks like a baroclinic signal since we're talking about movement of the thermocline. So next we wanted to ask, is variability related to barotropic or baroclinic processes? And part of why you might do this is because it possibly lends to some predictability, because, for instance, barotropic processes tend to follow topography. So this is a little reminder on GFD, if you don't remember. If we're talking about a barotropic flow, we have a one-layer system, so by potential conservation of potential vorticity, F over H is conserved. The Coriolis force over the depth of the ocean has to be conserved. So if we had flow moving eastward here in the southern hemisphere, and it comes to a seamount where H decreases, then the absolute value of F has to decrease as well. So this flow is going to move into the board or equatorward and kind of go around this seamount. So you can imagine it from above looking something like this, where we have flow moving eastward, then it'll move north, and then south, and then it'll move back eastward. So because of this, barotropic processes are very confined by the topography. Baroclinic processes, on the other hand, here we're talking about things like Rossby waves and eddies that would be propagating in from the east, and they don't have to follow topography because we now have a thermocline and we're not talking about a one-layer system, and the anomalies also tend to propagate more slowly. So here we're talking about something where the slopes of isopycnals change, and that impacts the shear in the flow. So to try to get an idea what's happening, we can take 1,000 meters as the approximate depth of the thermocline and look at velocity anomalies above 1,000 meters and velocity anomalies below 1,000 meters. So here those are shown in a scatter plot as the red points. And if we had purely barotropic flow, we would expect the velocity to change the same in both layers. So points would fall along this line here, And then in a first mode baroclinic flow, there would be, the points would lie perpendicular. So in other words, if there's a positive anomaly in one layer, there'd be a negative anomaly in the other. And what we see is something kind of in between those two. So it looks like both baroclinic and barotropic processes are occurring. But this is something I'm investigating further, and if people have suggestions for what to look at, please let me know. We can also try to look at this in a time series sense. So here, now in red, we're showing the total velocity of the upper layer. In black is the barotropic velocity, and in green is the baroclinic. And what it looks like is in the upper layer, the flow is largely barotropic. If we plot the lower layer, now in blue we have the lower layer velocities, in black is the barotropic component, and in green is the baroclinic. And the lower layer looks less barotropic than the upper layer, which is counterintuitive from GFD, and it's also the opposite of what's seen in the Kuroshio, for instance. I've been thinking about this a lot, and I think it might be because the Agulhas Current is very equivalent barotropic in structure, as noted by Elipo and Beal 2015. So I'm not really sure how that impacts all of this, and it's something I'm still thinking about. Okay, so lastly we want to ask, can we assume a linear relationship between volume and temperature transport and just measure volume transport? This would be a lot easier to do. So in the Florida current, you can do this, and you get a root mean square error of 0.11 petawatts. So here's a scatter plot showing the volume transport against the temperature transport. And you can see the points all fall very well along a line. We can plot the same thing. We have the box volume transport against box temperature transport, and then jet volume against jet temperature transport. And we do see a linear relationship, generally speaking, but the points tend to fall a little bit farther from the line than in the Florida current, so we get an RMS error of 0.25 petawatts. These are also color-coded by the day of year to try to see if we could pick out a seasonal cycle here, and we can't. But that might be due to the lack of measurements we have in the upper 500 meters, and also we only have 25-month time series. It's kind of hard to get an annual cycle out of a 25-month time series. We can also look at the relationship between the volume transport and the transport-weighted temperature. So here's the volume transport against the transport-weighted temperature for the box measurement, and then the same for the jet measurement. And generally what you see, there's a nonlinear relationship, but when the current is stronger, so over here, stronger southward, it tends to be colder. And when it's weaker, it tends to be warmer. This does break down a little bit for really low transport values. This is very different than what's seen in the Florida current. So this is the same thing in the Florida current, volume transport against transport-weighted temperature, and they did not observe any relationship here. The other thing to note is that we have transport-weighted temperatures varying from 9 degrees Celsius up to 20, and they saw variability from 18 to 21 degrees Celsius. So we're seeing much higher variability. So we can ask, why is that? Why is our transport-weighted temperature so variable? And also, why do we see this different relationship between volume transport and transport-weighted temperature? And to answer that, we can go back to our composites of the strong temperature transport times and weak temperature transport times. And what we see is this whole deep region with cold water has southward flow during the strong temperature transport times, and it has weakly northward flow during the weak temperature transport times. So in other words, what we're seeing here is when the Agulhas current strengthens, it deepens. It also broadens a little bit, so the current's about 250 kilometers wide when it's strong, and it's only about 200, maybe 180 kilometers wide when it's weaker. But I think that largely the cooler temperatures when the current is stronger have to do with these really cold waters being transported southward when the current is stronger. And in comparison, the Florida current can't broaden or deepen because it's very confined by topography. So revisiting our scientific questions, how does the temperature structure of the Agulhas current vary on seasonal and shorter timescales? It varies with meanders, which explain the most variance locally. So if you're at any point, most of the variability in temperature will be explained by meandering. It also varies with a deepening of the southward flow, which explains the most variance in the full current temperature transport. So the second EOF has more impact on the integrated transport of the current, whereas the first one has more impact on the temperature at any given point. And it also varies with a seasonal cycle, which is mostly confined to the surface, although there are some deeper signals as well. How much heat does the Agulhas current carry? In the mean, it carries 3.65 petawatts, with a range of 0.2 to 6.3 petawatts southward. And this is 3.3 times the temperature transport of the Indonesian through flow, and also larger than the temperature transport of the Florida current. And it confirms that the Agulhas current plays a large role in the full basin heat transport. What dynamic processes cause variability in the Agulhas current temperature transport? It seems like there are both barotropic and baroclinic processes going on, but this is still something that we're investigating further. And how well can we estimate the temperature transport of the Agulhas current using only the volume transport and a mean temperature? We get a root mean square error of 0.25 petawatts. This is a larger error in the Florida current, likely due to the more highly variable transport-weighted temperature that's caused by a deepening and a broadening of the southward flow. The full basin heat transport of the South Indian Ocean is somewhere between 1 and 1.5 petawatts. So this error that you would get from not measuring the temperature of the Agulhas current is potentially 25% of the signal. So I wouldn't say it's negligible. Maybe it's also not huge, but a 25% error is definitely a significant error source. So that says that it's important to measure the temperature of the Agulhas current if you want to resolve the full basin heat transport to better than a 25% error. Okay, full basin heat transport. This is a work in progress. So the fog is representing the beautiful results that you can't see yet. You have to come to my defense. The scientific questions here are: how much heat does the South Indian Ocean transport southward? Is there a seasonal cycle to the South Indian Ocean meridional heat transport? And what controls seasonal and shorter-term variability in South Indian Ocean heat transport? So the method is we're going to combine the Agulhas current temperature transport that I just talked about with an Argo and sea surface height mapping of the South Indian Ocean. So let's go into the Argo and sea surface height mapping of the South Indian Ocean. This is a paper that was published last year in GRL on the seasonal cycle of the South Indian Ocean subtropical gyre. And there's a recently deployed Argo float. So the scientific questions of this paper were: how large is the seasonal cycle of the gyre flow of the South Indian Ocean? Is this seasonal cycle caused by anomalies at the eastern or the western boundary? And can seasonal variability explain any of the observed gyre strengthening between 1987 and 2002? So going off that last point, previous studies have found a multidecadal strengthening of the South Pacific gyre. So we could imagine that something similar might be happening in the South Indian Ocean. And this has been reported by one study, Palmer et al. 2004, who found a strengthening of the South Indian subtropical gyre between 1987 and 2002. But they were using data at 2 points in time, and these data in 1987 and 2002 were taken at different times of year as well. So we wanted to ask, can we use Argo and satellite data to contextualize this strengthening? Is any of it potentially caused by seasonal variability, or does it seem like something longer term? So to do that, we mapped Argo and sea surface height data across this black line shown here. The data from the 1987 and 2002 cruises are shown in the gray and black shapes here. So we are located a little bit south of that. The reason we did it further south is because we have data of the Agulhas current right here. So we want to be able to connect what's happening across the entire basin. Then in orange are Argo profiles during one particular month, and the darker orange profiles are within 150 kilometers of that black line. So we want to see how our Argo coverage was. So we look at the number of profiles in longitude bins that were within 150 kilometers of that black line in every month. And we can see there were a lot of gaps in the coverage in the early 2000s, but generally speaking, since about 2007, there has been good coverage of the South Indian Ocean. So we choose to look at the data from 2007 to 2016. And then the method, following Hobbs and Willis 2012. I'm not going to go into all the details, but you can read the paper or ask me a question. We used objective interpolation to map the Argo temperature, salinity, and density in quarter degree by quarter degree bins monthly. And the sea surface height data is used to suppress impacts of the unresolved mesoscale variability. And we did have a hydrographic crossing in 2009. So at that point in time, we can compare our Argo sea surface height data to the hydrographic data directly to come up with an error. So the bars here are showing transport in different longitude bins, and then the lines are showing the integrated transport across the basin. And generally they agree very well. So we come up with an error of 3.1 spare drips, which is a combination of this sampling error as well as a statistical error. So what we end up getting for every month is temperature, salinity, and geostrophic velocity across the South Indian Ocean. So here I'm showing an example with temperature. So this is what the sea surface temperature looked like in a particular month, and then this is the depth section across the black line shown here in that same month. And we use that to construct the seasonal cycle. So we run into a problem of how do we define the gyre. So the first thing we do is we follow Palmer et al. 2004 because we're trying to contextualize their study. So they define the gyre as the geostrophic transport relative to 2000 decibars between 35 degrees east and 110 degrees east. So if we use the same definition, we get the seasonal cycle shown in black here with the error shown on either side in the dashed lines. And then the 1987 data from Palmer et al. Is shown in green with their error bars around it, and then the 2002 data in blue with their error bars. So what we end up seeing is a seasonal cycle that's very annual with peak-to-peak amplitude of 10 spare drips. And the seasonal cycle cannot explain this strengthening between 1987 and 2002 because if we look at the times of year those were taken, according to our seasonal cycle, the geostrophic gyre transport should be very similar in those times of year. The kind of issue with that definition is if we look at where 35 east to 110 east are, that's the green line here, it doesn't cross the entire basin. So it's missing some flow here that's still offshore of the Agulhas Current, and then some flow in the east as well. And so we decided to do a definition including all of that. So if we define the gyre as the full basin flow east of the Agulhas Current, we get something different. We get this seasonal cycle shown in black here that's very semi-annual. Also shown here is the seasonal cycle in the Agulhas Current, upper 2,000 meter transport. And then in blue is the seasonal cycle if we just assumed mass balance between the Agulhas Current and the seasonal cycle of the Indonesian through flow. So what we see is a semi-annual cycle of 6.4 spare drips. And we also see that mass balance between the Agulhas Current and the Indonesian through flow matches very well with what we see. So that suggests that potentially a large part of this is just described by mass balance between the inflows and outflows of the basin. And lastly, we want to ask what causes this semi-annual cycle. So to do that, we looked at dynamic height anomalies. These are dynamic height anomalies in 3-month bins from the same 10 years of data. And if we look at the western boundary, we see that there's a peak in dynamic height in January, February, March, and then there's a minimum in July, August, September. And if we look at the eastern boundary, we see a peak in April, May, June, and a minimum in October, November, December. So at each boundary, there seems to be a seasonal cycle occurring in dynamic height, but the eastern and the western boundaries are out of phase with each other. So what we find is that both eastern and western boundary annual cycles contribute, but because these annual cycles are 90 degrees out of phase, when we look at the transport between the two endpoints, we get a semi-annual cycle. So going back to our scientific questions, how large is the seasonal cycle of the gyre flow of the South Indian Ocean? 6.4 plus or minus 3.1 spare drips peak to peak, and it's semi-annual. Is the seasonal cycle caused by anomalies at the eastern or the western boundary? It seems to be caused by both, but they're 90 degrees out of phase. And can seasonal variability explain any of the observed gyre strengthening between 1987 and 2002? No, which implies that we're seeing, or that Palmer et al. 2004 saw an interannual or longer strengthening of the gyre. Okay, going back to heat transport of the full basin. So the methods, like I already mentioned, we're going to combine the Agulhas Current temperature transport with the Argo sea surface height mapping of the South Indian Ocean that I just described. We also need to add in a few pieces. We need to add in the flow below 2,000 meters, since Argo floats generally only go to 2,000 meters. And to do that, we'll use mass balance as well as deep hydrographic data. We also need to add in the Ekman transport, which we can do with ECMWF winds. And we need to make some assumptions about the size of the Indonesian through flow coming into the basin and about the eddy heat transport. So in terms of an equation, if Q is our heat transport here, the full basin heat transport is Q ASCA, the heat transport of the Agulhas Current, plus the heat transport of the upper 2,000 meters from Argo, plus the heat transport below 2,000 meters from our mass balance and deep hydrographic data, plus a Q Ekman from the winds, and then plus a Q eddy, which likely we will assume is small because we don't really have a better way to calculate it. And that's stuff I'm also working on currently. So I want to say thank you to a bunch of people. First off, the Agulhas group, as well as the ASCA project, which funded me. The UCT faculty and students who were super helpful when I was teaching at University of Cape Town. US Go Ship, who took me to the Southern Ocean, which was amazing. And my PhD committee. And with that, I will take any questions. Yeah.
You didn't talk about, and I'm sorry, I don't remember Lisa's earlier paper, what causes the meanders in the Agulhas Current?
So there tend to be anomalies that propagate from upstream of the current across one of two pathways. So there's a Rossby wave guide going across the Indian Ocean, and you can track the sea surface height anomalies back across there, or across at the equator. Yeah.
For the result that you were showing about how the seasonal cycle didn't play well, so it's probably longer term variability, is it possible that there's some influence from the PDO in that region, or is there like an individual multidecadal mode variability in that region?
I don't know very much specifically about the PDO and how it impacts the Indian Ocean. I do know ENSO has been linked to some variability in the Agulhas Current specifically, so it is possible that there's some link to some sort of interannual climate mode. I don't know which one it would be specifically or how, but it's definitely possible that there's something. Yeah.
So the southern angular mode of the southern winds have been shown to affect the ventilation, that is the uptake of oxygen and other gases in the southern hemisphere gyres, and that, which is part of Reming's work, and so that surely should be something that's affecting the strength of the gyre.
Yeah, so the winds are definitely impacting the strength of the gyre, and I should have put a reference to it, but there's another paper that talks about the strengthening of the gyre using changes in the oxygen data between 1987 and 2002. I don't think anyone has looked to see if that strengthening has continued into the 2009 data.
McMonigal's paper?
Yeah, McDougall, yeah. Or no, McDonough. Yes, there we go.
Thank you.
Yeah, I think it's like McDonough 2008 potentially. I don't think anyone's looked at the 2009 data to see if that continues things, and then we will also have data in 2020. So that's very much an open question.
I actually look at continuing the next decade, and it doesn't seems to drop.
Interesting. Okay.
Fine, 2017.
Ah, okay. I will check that out.
Do I need to say something? No.
No, we have one more question.
This might be a point that you said, but maybe I missed it.
Yeah.
When you were detailing the upcoming actions, you were talking about the South Indian Ocean heat transport.
Mm-hmm.
Beginning of your talk, you were careful to distinguish between temperature transport and heat transport. So
Yeah.
will it really be a heat transport that you're computing? Or
Because of the Indonesian through flow?
So it would be a heat. So it would be then. Will it be a heat transport relative to that box? So the box would be sort of the Indian Ocean north of that line.
Yeah, so that is one of the difficulties is kind of how do you deal with the Indonesian through flow, which I haven't quite decided what I'm going to do. If you had a time series of temperature transport at both lines, you could look at convergences of heat, which would probably be the best way to go. I think there is data of the Indonesian through flow through the same time period, but it hasn't been published yet, so it's kind of difficult to do that. So probably it'll be a heat transport, but considering that approximately 15 sphere drips that is moving southward due to the Indonesian through flow. So it won't technically conserve mass, likely. That's probably what we'll do.
And don't forget the Indonesian through flow has seasonal, and so
I know. Every type of variability.
Fun.
Yes.
Okay, then, thank you.
Thank you.